So today we will look at solutions to special problems for incompressible materials. So one formula that I will present for orthogonal coordinate system. So for orthogonal curvilinear coordinate systems, the deformation gradient is given by Fij is equal to Hi by Hj from del chi I hat by del eta j. So this Hi are the scale factors associated with the curvilinear coordinate system for the deformed configuration. And Hj are the scale factors for the curvilinear coordinate system for the reference configuration. So typically this capital letter is used for the reference configuration, and this small letter is used for the small index is used for the deformed configuration here. So you can imagine that your x, that is the material coordinates, are parameterized in terms of this eta1, eta2 and eta3. So that is the same as this eta j. So I and j are running from 1 to 3. So I equal to 1 to 3 and j is also 1 to 3. So these are the 9 components. So I will not go into the derivation of this equation here about how to get this deformation gradient. That is again there in the book. So we will directly see how to use this particular formula. So you can also directly use this particular formula. So even these scale factors I will be giving if required for any given coordinate system here. So typically when we present some examples, you will get to see how to use this particular formula here. So this x is a function of eta1, eta2, eta3, which are the curvilinear coordinates that are being used for the reference configuration, and your and suppose if xi equal to xi1, xi2 and xi3 are the coordinates, curvilinear coordinates that are being used to parameterize the deformed configuration, then that is equal to chi hat of eta1, eta2, eta3. And so basically you are taking the gradient of this particular mapping here, so as to reach to the deformed configuration, the position vector in the deformed configuration. So as I said that we will look at examples, and then maybe it will become clear how to use these particular equations here. So first example that we will do is bending and stretching of a rectangular block. Bending and stretching of a rectangular block. So this is x and y. So this corner is x1 minus y0, this corner is x2 y0 here, and it goes into this deformed configuration. So let us look at the deformation corresponding to this. So the deformation is given by r is equal to under root of 2ax, then theta is equal to b times y, and z is equal to z divided by ab. So here this z is extending into the board here. Okay, so that is the z coordinate here, and this you can see that lines of constant x, right? So suppose if I take a line that corresponds to a constant value of capital X, then that goes to a value of constant r. See, because if x is constant, then you can see that r is also going to be a constant. So, so all these lines, right? So this outermost line here goes into this particular line here. Then this particular line here goes into this radius r1. And so on. So each line, which is a constant x, goes into a constant r line. Then similarly, here you can see that a constant y line goes to a constant theta line. So that means any line, if I take here, which has a constant y, that goes to a constant theta line on this in the deformed configuration. Right? So here, this top line here, that goes into this particular line. This line goes into this particular line. So basically, through the application of some moment or some force, you are bringing it from this reference configuration to this deformed configuration, and this is the mapping that we are using to get there. Yes, so let us look at now the scale factors for this one. So you are you can see that it's, we are using a Cartesian coordinate system for the reference configuration, and we are using a cylindrical coordinate system for the deformed configuration. And so the scale factors for that are so Hj is just 1, 1, 1. Okay, so that is just corresponding to the scale factors for a Cartesian coordinate system, and your Hi are 1, R, 1. So those are the scale factors for the cylindrical coordinate system. So basically, if you see, when you write a gradient, right? So suppose if I want to write del phi by del r, then del phi by r del theta, and del phi by del z, right? So this coefficient, so this is like 1 by 1, then this coefficient is the scale factor here. So this coefficient here, r, is the scale factor corresponding to theta, and then again this 1 is the scale factor corresponding to this. In the case of a Cartesian system, you would simply write del phi by del x, del phi by del y, del phi by del z. Correct? So that here the scale factors are 1. So I mean, of course, there is a systematic way of deriving the scale factors, but I will not go into that. So as I said, that you can take a look at it in the book. So all the various appendices, they will list the scale factors for each of these coordinate systems. But as I said, I will give the scale factors if required in the assignments or in your exams. So now let us find out what is the deformation gradient corresponding to this deformation here. So this F you will get as diagonal of A by R, then BR, and 1 by B. Okay. So you can see that actually this factor here is adjusted so that the determinant of F will be equal to 1. See, we are now all these solutions that we are considering are for incompressible materials, and so all the deformations that we are going to consider are isochoric or volume preserving, right? And so your det F has to be equal to 1 here. So this, so let us just note that. So if you take the determinant of this, so determinant of F is equal to +1. So this diagonal means that this is a diagonal matrix with A by R as 1, 1, BR on 2, 2, and then 1 by AB as 3, 3, on all the other entries are 0. So basically it's just a diagonal matrix. And so as I said that this factor here is adjusted so that you get determinant of f is equal to plus 1 here. Fine. Then once you find out the deformation gradient, then after that it's a very routine exercise. Then you find out what is the left Cauchy-Green strain tensor, so that is B. Then you substitute that into the constitutive relation, that is tau is minus pi plus beta minus 1 b raised to minus 1, that is B inverse, plus beta 1 b, and so on. So then now you can recover all the stress components once you know what the deformation gradient is. So let us calculate those things here. So B now would be, so B is equal to FF transpose. So FF transpose, so that is equal to diagonal of A square by R square, A square by R square, then B square R square, and 1 by A square B square, and B inverse would be equal to diagonal of 1 R square by A square, 1 by B square R square, and A square B square. So this would be the B and the B inverse. And we can see that tau plus Pi is a function of R alone. Okay, so that is because, so if you recall, tau is equal to minus Pi plus B inverse plus beta 1 times B. Correct. So tau plus Pi, like tau plus Pi is equal to B inverse plus B beta 1 times B. And so from this you can see that tau plus Pi is a function of R alone, because B inverse and B are functions of R alone, right? So tau plus Pi is a function of R alone, right? And then we know that in addition we also have that tau R theta is equal to tau R z is equal to 0. Correct? So all those assumptions that I had listed in the last class, those are satisfied, and hence we can apply the results for the wedge type, annular wedge type region that I had shown in the previous class here. So that we can use directly for this one. And if we assume now that this surface is traction free, like so R equal to R1 is traction free, then as I said, we have already noted the formulae for the various cases. So let me just recall those formulae here. So you will get now that tau R is equal to integral from R2 to R1 to R of beta 1 minus beta by A square B square times minus A square by R square plus B square R times dr. And then tau theta theta is equal to tau R plus tau theta theta minus tau R. So as I said, this trick is used to eliminate the pressure, and this is equal to tau R plus minus of R square by A square plus 1 by B square R square beta minus 1 plus minus A square by R square plus B square R square times beta 1. And similarly tau ZZ is equal to tau R plus tau ZZ minus tau RR, and that is equal to tau RR plus A square B square minus R square by A square beta plus 1 by A square B square minus A square by R square times beta 1. So this is the expression for this one. And your beta minus 1 and beta 1 are functions of invariants of B. So I1 of B and I2 of B. So that you can find a trace of B itself and trace of cofactor of B. So from that you can find out the that the beta minus 1 and beta 1 are going to be functions of these things. Fine. And then we also saw that when the surface R equal to R1 is assumed to be traction free, then R is equal to 0. So this R is this particular force here, right? The R was the force that is applied on these edges here. So that R is equal to 0 if and only if tau R and R equal to R2 is equal to 0. So that is the result that we had shown last time. So we'll use that result here now. So then surface, when the surface R equal to R1 is traction free, then R is equal to 0 implies that tau RR and R equal to R2 is equal to 0. So the necessary and sufficient condition that the bending is caused only by a moment. That means there is no axial force, there is no tangential force, is that the integral of R1 to R2 of beta 1 minus beta minus 1 by a square b square times minus a square by r square plus b square r times br is equal to 0. So this is the necessary and sufficient condition. Necessary and sufficient condition for the deformation to be caused by a bending moment alone. So this bending moment is at M, whatever I indicated here. This is the, so basically this deformation is caused by a bending moment alone if this condition is satisfied. Okay, so that means, because then this condition is basically saying that this R is equal to 0. So that is the condition here, that is what is written here, that tau R and R equal to R2 is equal to 0 here. So as I said that then now you can substitute various kinds of models, so Mooney-Rivlin or whatever, Arunda Boys or various kinds of models you can substitute into this to check whether this condition is satisfied, and then so you can specialize now these results for particular constitutive models. So as I said that Mooney-Rivlin or Ogden or whatever model, because then the coefficients will depend on what model you are using, and then you can find out special results for these for particular constitutive relations here. But I have already mentioned that actually, I mean, in your assignments and tests, you need not follow this particular approach. So try to do things from first principles. So that means just write out the equilibrium equations, try to solve them, and see that your boundary conditions are satisfied. So you don't have to learn all these tricks. As I said, all these tricks are done here because he was trying to solve it for any arbitrary constitutive relation. But in your assignments or tests, I will be giving a specific constitutive model, and so the expectation is that you work it out from first principles rather than learning all these tricks. So all these tricks are not I mean, you don't require to memorize any of these tricks that I have used in this, but while deriving these particular solutions. So, for example, so you saw that the tau zz, I wrote it as tau r plus tau zz minus tau r. So all those tricks, you don't need to do know those kind of tricks here. So directly you can solve it from first principles. Fine. Then let us look at another example. So this is the torsion and inflation, etc. of an angular wedge. So look at this example. So here the deformation is given by r is equal to under root of ar square plus b theta is equal to c theta plus bz, and z is equal to e theta plus fz, and a times cf minus be is equal to 1. So this condition here is the isochoric deformation condition. That means the volume preserving condition, that your det f has to be equal to 1, because we are assuming that again the material is incompressible, and so this is the constraint here. So so here in this particular case we are using a cylindrical geometry for the undeformed configuration or the reference configuration, and cylindrical coordinate system also for the deformed configuration. So in this particular case you will get that hi is equal to 1r1, and your hj will be equal to 1r1. Okay, so in this particular case these will be the scale factors, and then using these scale factors then you just simply differentiate it. So del r by del r, and then you have to multiply it by the scale factors, that hi by j and so on. So you will get that f is equal to ar by r 0 0, then 0 cr by r, then e by r, because this should have been dr, then 0 e by r and f. So this is the deformation gradient, and then now you can find out what is b and b inverse and so on. So b is equal to ff transpose, and then similarly from this now that you can just invert this particular matrix, invert in order to find b inverse. So I will not go into all the details about this particular thing, but what you will find is that again tau plus pi is a function of r. So tau plus pi is f of r again. So same. So again it satisfies all the assumptions, and tau r theta is equal to tau rz is equal to 0. So all the assumptions that we had made for the angular wedge, they are again satisfied, and then again we can apply all the results that I derived earlier for this particular problem here, and then I can derive now the expressions for tau r, tau theta, and so on. So I will not go into all the details about the derivation, but just let me mention one special case here. So the special case is that of a pure torsion. So special case of this particular deformation. Let us look at that. So special case is a pure torsion of a hollow circular cylinder So you will get that you set A is equal to 1, then B is equal to 0, C is equal to 1, E equal to 0, F equal to 1, and theta naught equal to pi. Okay. So in that deformation, if you set all of these things, then you will get the case of pure torsion. So basically, if you see your theta expression, right? So now your theta is d times z. So that if you see theta now is equal to c theta, so that is theta plus dz. Correct. So basically, you can see that when z is equal to 0, then theta equal to theta. So the bottom surface is fixed, and then your top surface, right, it is twisting, right, in its own plane like this. So that is what this equation says basically. So it is increasing linearly with z because of this particular factor here, and of course that deformation is getting added to the original theta. Whatever was the original theta, that is getting added to that. But on the bottom surface, it will be z will be 0, and then you will get that angle is same. So the bottom surface is fixed, and then linearly that angular deformation is increasing linearly with z. So that is, as I said, that so this is a special case of a pure torsion of a hollow circular cylinder here. So in this particular case, you will see that the tau r. So let us look at the stresses that you get in this particular case. So you get tau r is d square integral of beta 1 r times dr. Then tau theta theta is equal to tau r plus d square beta 1 times r square, tau zz is equal to tau r plus d square beta minus 1 times r square, and tau theta z is equal to d times beta 1 minus beta minus 1 times r. So this you can say is d times mu hat times r. So this factor we are calling it as mu hat. So mu hat is equal to beta 1 minus beta minus 1. And then so basically now you can find out the stress distribution and ensure that all the traction boundary conditions are satisfied, and so on and so forth, right? Then the torque that you get, so I derived the expression for the torque earlier. So that torque now T is equal to 2 pi times d times r1 to r2 of mu hat times r cube times dr. Okay, so this is the expression for the torque. Okay, so these r1 and r2 are the radii in the undeformed or in the reference configuration. So this is r1, and so this is the original configuration, right? So r1 and r2 are the original radii before the application of the load, but the integral is expressed in terms of this r1 and r2 here. Similarly, you can find out what is the normal force that is to be applied, and so this is something. So these are some features that are different than linear elasticity. Okay, so here you can see that I mean, if you take the linear case, then we can get a pure torsion just by applying tractions on the top and the bottom surfaces. You need not apply normal, only tangential tractions on the top and the bottom surfaces. So just you are twisting it, right, in this particular way. So you have a cylinder, you just apply tangential tractions on the top surface and on the bottom surface, and you can get a twisting. But in this particular case, so in the nonlinear case, you also have to apply a normal force. So that means in this particular direction. Okay? So this is one peculiarity of the nonlinear case. So in this case, the n is not equal to 0. So this is, let us call it as n. So in the nonlinear case, you will get all these kinds of effects. which you don't see in the case of the linear elasticity here. Right, and so even that can be calculated, but I will not go into the detailed expressions. Again, those you can take a look at it from the book, and then you can again specialize it to particular models. So whether it is Mooney-Rivlin or Venn model or whatever model, by actually writing out this beta 1 and beta minus 1 in terms of the invariants, right, of B and so on. So then you can get the results for special constitutive models. Okay, so I think this sort of completes this topic about closed form solutions. There is one example in your assignment of a spinning cylinder, so you can solve that. That will give you a further idea about these closed form solutions here. So with this, actually we will move to the next topic, which is linearized elasticity now. So basically all of you have studied linearized elasticity in some course or the other. So in this course I will not solve special examples of problems in linear elasticity, but I will merely show how to obtain the equations of linear elasticity from the nonlinear equations by a very systematic linearization of the governing equations. And so we have already seen that every single aspect of the elasticity problem is nonlinear, right? The governing equation is nonlinear, that is del dot fs plus rho v. So del dot fs, so that f shows that there is a nonlinearity in the linear momentum equation. Then the boundary conditions are nonlinear because your traction boundary conditions involves a cofactor of f, so that we have seen. Then the strain displacement is nonlinear because you have the half of del u transpose del u term in the strain displacement relation. The constitutive relation is nonlinear, right? Because we have seen that can depend on I, B square. So that relation is nonlinear. So every single aspect of the nonlinear elasticity problem is nonlinear. And so what we are going to do is that we are going to obtain the equations of linearized elasticity. So the correct term is not linear elasticity but linearized elasticity, in the sense that we are actually linearizing all the nonlinear equations in order to obtain the equations of linearized elasticity. And so let us take a look at how to go about doing that. So basically my purpose is just to derive the governing equations for linearized elasticity, but I will not be solving special problems in the case of linearized elasticity in this particular course here. So let us look at the linearized elasticity. So let f hat of h be equal to h. So this is just sort of mapping of a tensor into itself. So we will need that. So that is the reason I am introducing this particular mapping here. So this f, which is now the deformation gradient, that is equal to I plus del u. So this I can write as f hat of I. So f hat of I will be I, and so that is this particular term here, plus d of f hat of I in the direction of del u. So I am just using the notion of directional derivative in this particular case. So this d of f hat in the direction of del u is going to be del u itself. So let me write that. So d of f hat evaluated at I in the direction of del u is equal to del u. And so so when we now linearize the various strain measures, we will use this particular result here. So so the linearizations. Linearizations are going to be carried out about f is equal to identity, which is the reference configuration. So remember, in linearized elasticity, suppose if this is your reference configuration, we are considering only very small perturbations, right? Only small deformations of the reference configuration, right? And so we have already made the assumption that u is small compared to x, capital X, and the deformation gradient components are also small in some norm sense, right? So that we have already seen. So here we will use the linearization about f equal to I, because we are considering only small perturbations about the reference configuration. So f equal to I corresponds to the reference configuration, and so we are going to consider, as I said, only very small perturbations about that. So d now of E evaluated at I in the direction then u is equal to half of f hat transpose evaluated at I times d of f hat of I in the direction del u plus d of f hat transpose evaluated at I in the direction del u times f hat of I. Okay, so because everything is being done at the identity tensor, right? This is f equal to I here. So this is, so f hat of I is identity tensor, and d f hat of I in the direction of del u is del u. So you will get that this is equal to half of del u plus del u transpose, right? So because there is a transpose here, so you will get this. And so this is nothing but epsilon, which this is the linearized strain tensor, which we have denoted by epsilon in our when we studied kinematics. So I denoted this small strain tensor by epsilon here. Then similarly, now let us carry out the linearization of the Unmanned strain tensor. So d of f inverse identity in the direction of del u is equal to minus f hat inverse times I times del u times f hat inverse evaluated at identity tensor. So this is just, this relation is just obtained by taking the derivative of this particular relation, f inverse is equal to identity. So apply the product rule while taking the derivative of this one. Then this is what you will get. And since f is invertible, we can write this particular relation here. So again, f hat or identity is identity, and f hat minus inverse of identity is also identity. So you will get del u. So you will get del u here, and then similarly you will just one second. So this is actually minus, sorry. So this is minus of del u. So you get minus of del u here. So if I now linearize the Unmanned strain, let us do that here. So d of E bar at identity in the direction of del u is equal to minus half of f inverse transpose evaluated at identity d of f inverse identity in the direction of del u plus d of f inverse transpose evaluated at I in the direction del u times f hat inverse times again evaluated at identity here. And so if you evaluate this particular expression, you will get that is equal to half of del u plus del u transpose, which is also equal to epsilon. So if you recall, I had made this statement when we were studying kinematics that there are an infinite number of strain measures in the nonlinear context, but when you linearize all of these nonlinear strain measures, you get only one strain tensor. So that is why if you take a book on linearized elasticity, typically they will only introduce the linear strain tensor, which is this one, like books by Timoshenko and Goodyear and so on and so forth. So this is the only strain tensor that needs to be introduced in the linear context, because all the linearization, right, and we will see some more strain measures, the linearizations of all of these non-linear strain measures, they will all collapse into this epsilon, which is the linearized strain tensor here. Okay, so let us look at some more strain measures. So let us look at U now. U is the stretch tensor. So let us look at that. Whatever occurs in the polarity position, F equal to RU, so that U. Let us look at the linearization of that particular tensor here. So we know that U square, so C is equal to U square is equal to F transpose F. So if I now take the derivative of this, so this is U at F equal to I times D of U evaluated at I in the direction of del U plus D of U evaluated at I in the direction of del U times U evaluated at F equal to identity is equal to D of F transpose I in the direction del U. Then this is just identity, because you are evaluating F at identity itself, so that is just identity plus identity transpose times D of F evaluated at I in the direction del U. And so if you do this, and so U at F equal to identity will be identity. So this will be again identity, and so what we will get is that D of U evaluated at identity in the direction of del U is equal to half of D of F in the direction of I. So here, okay, this F hat missing here. So D of F hat of I in the direction del U plus D of F transpose, so D of F hat transpose in the direction del U. And so that is again equal to half of del U plus del U transpose, and that is equal to epsilon again. So again you can see that even for the stretch tensor we will get same result. And then similarly you will get that D of V of I in the direction del U is also equal to epsilon. So to summarize, basically no matter which strain tensor you look at, you will always get back the linearized strain tensor upon linearization. So you don't need to consider multiple strain measures in the linearized context. Okay, so just this epsilon if you introduce, that is good enough here. So okay, then let us find now the linearization of the R part, that is the rotation part in the polarity composition. So F is equal to RU, right? So we found out the linearization of U is epsilon itself. So now let us find out what is the linearization of the R part in that, the rotation part in that. So if I now differentiate F is equal to RU, so I will get that D of F hat of I in the direction del U is equal to R evaluated at F equal to identity times D of U in the direction del U plus D of R in the direction del U times evaluated at F equal to identity. So this is again evaluated at F equal to identity. So if you now simplify this particular expression, then what you get is that D of R evaluated at I in the direction del U will be equal to half of del U minus del U transpose. Okay. So there is a minus sign now, so this is not the epsilon now that you get. So So this half of del u minus del u transpose is a measure of rigid rotation of an element. Okay. So in the linearized context, basically, if you take an element here, this is a measure of how much this particular element rotates. Okay, so this half of del u minus del u transpose is a measure of rotation in the linearized context. Okay, so but this is of course a local rotation. So I mean the whole body need not be rotating, but this is a measure of how much at each point an element is rotating. So that measure, I mean that d of r in the direction of del u is a measure of that rotation here. Fine. Then what about det f now? So let us look at the linearization of det f. So you have now f again is equal to I plus del u. So this implies that det f is equal to det of I plus del u times cofactor of f plus order of u term. So that is we have already seen this expansion for the determinant. So this is equal to 1 plus del u times so this is evaluated at input identity. Okay, so this is so this you will get as the cofactor of identity is identity itself. So you will get this plus order u term, so plus order of u. So this is equal to trace of del u. So basically d of j. So this is j. J is det f. So d of j in the direction del u is equal to trace of del u, which is equal to del dot u, which is also equal to trace of epsilon. So that is the result that you get. So in the linearized context, the change in volume per unit volume is del dot u. So that is so if you recall. We have this relation that dV is equal to J times dV naught, right? But in the linearized context, the change in volume per unit volume will be given by del dot U, not by the J itself. So that is one thing you have to remember here. So basically, you can say that delta V by V is this del dot U, the change in volume per unit volume will be represented by this particular constant. Fine. Then, what about linearized rigid displacement? So, that is what is the form of the displacement field so that the strain vanishes, and conversely, if the strain vanishes, then what is the form of the displacement field here? So we have this particular theorem now. So this is characterization of linearized rigid displacement now. So characterization of linearized rigid displacement. So by linearized we mean in the context of the linear theory of elasticity. So the displacement field U is a linearized rigid displacement. Or also infinite rigid displacement. If and only if U equal to W of T times X plus C of T. W is of course a skew symmetric tensor here. W of T belongs to skew, and this C of T is just a vector in R3. So you can also write this in the form omega of T cross X plus C of T, because where this omega of T is the axial vector of the skew symmetric tensor W of T. So actually the proof of this one is very similar to the characterization of rigid motion, the second characterization of rigid motion in terms of the velocity. So if you recall, we proved that V is equal to W of T times X plus C of T, right? And then we showed that del V plus del V transpose, right? So L in this case is equal to del V plus del V transpose by 2 is equal to this is D, I'm sorry about that. This is the rate of deformation tensor. So that is just del V plus del V transpose by 2 is equal to 0, because del V will be equal to W of T. So it's the same thing here, that basically you will get that del U is equal to, now this is with respect to capital X. So this was with respect to small x, this is with respect to capital X. So this is equal to W of T, and so this will imply that epsilon is equal to half of W plus W transpose is equal to 0. Right? And then conversely, if epsilon is equal to 0, then U has to be of this particular form. So as I said, that I'm just going to go refer you to the proof of this one, because the proof is just identical to the characterization of linearized motion. If you make the substitution that instead of small x, now you will have capital X. Then instead of V, you will have U. So just make these substitutions, and then basically the proof is similar to that one. So I will just note that here. So maybe so here I will just state it. So proof similar to characterization of rigid motion, to characterization of rigid motion. So 2, that means we are given 2 characterizations. So this is the characterization that I am referring to. Right? So as I said, just in place of small x, you will have capital X. In place of V, you will have U. Then in place of D, you will have epsilon, and so on. So just it's just a different set of variables. That's all. But otherwise, the structure of the proof is almost identical to that one. So I will not go through the proof of this particular thing here. So okay, we'll move to the next thing here, which is the compatibility condition. And so this is a very, very important topic here. There is a lot of confusion regarding this topic in the literature. So let us try to clarify some of the issues related to the compatibility relations here. So compatibility relations, let's look at those things now. So compatibility, relations. So strain field, epsilon. U transpose satisfies the compatibility conditions. Del cross del of epsilon equal to 0. So this is the curl of a second order tensor, now which we had introduced when we were doing the tensor part. And then conversely, so conversely, if the compatibility conditions, so let's call it a star. Compatibility conditions star are satisfied, and if the domain is simply connected, and if the domain is simply connected, then there exists a displacement field U that satisfies epsilon is equal to del U plus del U transpose divided by 2. And this field is unique, and U is unique up to a linearized displacement, up to a linearized rigid displacement. So by up to a linearized rigid displacement means we can add that W of t times x plus c, right? So because this just results in a zero strain, right? So basically you can always add this term to whatever displacement field you have, you can always add that, and the strain will remain the same. So up to linearized displacement, you can add this term to the displacement. But apart from this, so if you somehow suppress this particular part, then the displacement field is unique. Okay, so that is what it basically says here. Now another thing is that this domain being simply connected here. So that is also another important condition here. So just I mean, this domain being simply in the context of 2D, domain being simply connected means there are no holes in the structure. In the context of 3D, suppose if you take a hollow sphere, that is also a simply connected body. So basically, if you take a rubber band, okay, and you are able to shrink it to a particular, so if you take a stretched rubber band in any part of the domain, and if you are able to shrink it to a particular point without leaving the domain, then that region is called as a simply connected region. Okay, so for example, in the 2D context, suppose if you had a hole, right, and if I put the rubber band like this, right, then I will not be able to shrink it to a point without leaving this domain, because this part here is outside the domain, right? So in the 2D context, just having holes means that it is multiply connected. But in the 3D context, if you have a hollow sphere, then you can imagine that you are stretching this rubber band around the hole, but you can take it from the side, okay, side of the hole, because it is 3D now, and then you can still shrink it to a point. So you have to be very careful about this simply connected, multiply connected. In 3D, just having holes does not imply that it is multiply connected. But in the 2D context, at least, that is the implication that any hole means that's a multiply connected region. So okay, so what we are saying here is that if the domain is simply connected and if this condition is satisfied, then there is a unique U that will satisfy this particular condition. So there exists a U and it is unique also, which will satisfy this particular relation. Okay, but if it is multiply connected, then in addition to this, you need some additional conditions. Okay, so it is not that you don't require this, so you still require this, but in the case of multiply connected, additional conditions need to be given. But we will not again go into those details. So we will just consider the case of the simply connected domain here. So for multiply connected, there are additional conditions. Conditions need to be given. So just checking del cross epsilon equal to 0 is not enough in the case of a multiply connected. In case we have more conditions there. Fine. So let us prove this particular theorem now. So the first part of the proof is just an exercise in indicial notation. So let us show that. So basically del cross epsilon. So this is the proof now. So you are now given that epsilon is equal to half of del u plus del u transpose, and we are trying to show that del cross epsilon equal to 0. So this is just a sort of elementary exercise in indicial notation. So this is let me just carry that out. So this is ij, this is equal to epsilon I m n del by del xm of del cross epsilon times jn. Okay, so this is just we are using the definition of a curl of a second order tensor here, and then this is equal to epsilon I m n times epsilon jst del square epsilon st by del xm del xs. Okay, and then now you can write this as epsilon I m n epsilon jst times substitute now for epsilon because that is del u plus del u transpose. So you will get that this is del q of un by del xm del xs del xt plus del q of ut by del xm del xn del xs. Okay. Now here, so you will associate. Let us see this. So this is JST. So you associate this with this particular term here, okay? And then you see that you will now interchange S and T. So you are interchange S and T, S and T, and then use the fact that epsilon JST is minus of epsilon JTS. Okay? And so, but this order of differentiation can be interchanged. So this is the usual trick that we have played to show that this particular object is the negative of this particular object. And then similarly this part you associate it with this, and here you interchange m and n. Right? So here you interchange m and n, and so this part is also 0. So this is just, as I said, this is just a standard exercise in indicial notation. So basically what you will get is that this is equal to 0. So what that shows is that if epsilon is equal to half of del u plus del u transpose, then del cross epsilon is equal to 0. Now we have to show the converse implication that if del cross epsilon is equal to 0, then there exists a displacement field u such that epsilon is equal to half of del u plus del u transpose. So of course that proof is much more complicated than this one. So let us try to show that proof now. Yes, so let us show the converse now. Converse. So if S belongs to sim, then trace of del cross S is equal to 0. So first we will prove this. So this implies that trace of del cross S is equal to 0. So let us show that. So trace of del cross S is equal to epsilon I m n del of S I m by del of x m. So I'm just using again the definition of the curl of a second order tensor. If Tij are the components of a second order tensor, then Tii will be the trace of that particular tensor. So I am setting the second index j to I. So that is why you get this I is a repeated index in this particular case here. That is because we are finding the trace of this particular thing here. So this is equal to epsilon mni times del s ni by del xm. So what I have done here is that I have interchanged the indices n and I. So here what I have done is that n is interchanged with I. Okay, so that we can see that, and I also maybe used. Just give me 1 second. So this should be nmi. I'm sorry about this. This should have been nmi. So I've just simply interchanged the indices n and I, and then because they are dummy indices, so I can do that. And then now use the fact that epsilon nmi is minus of epsilon imn. So it is minus epsilon imn of del sin by del xn. So I'm using the symmetry of the tensor S. So Sni I can write as Sin, and so you will see that this object is the negative of the same object, and so it has to be equal to 0 here. So this is equal to minus of trace of del cross S, and so this implies that trace of del cross S is equal to 0 here. Fine. Then epsilon is a symmetric tensor, right? And so we will get that trace of del cross epsilon is equal to 0. So since epsilon also belongs to sim, we will get trace of del cross epsilon is equal to 0. And we are also given that del cross epsilon is equal to 0. So this is also given. So now you go back to some of the potential theorems that we did when we were discussing in the tensor part. So there we showed that if del cross epsilon equal to 0 and trace of del cross epsilon equal to 0, then there exists, so by one of the potential theorems, there exists a W. There exists W belonging to skew such that del cross epsilon is equal to del cross W. Okay. So we have shown that if del cross epsilon equal to 0 and the trace of del cross epsilon equal to 0, then there exists a skew symmetric tensor such that this part here, del cross epsilon, is equal to del cross W. So this part here now can be written as del cross epsilon minus W is equal to 0 here. And we have seen now that if del cross some second order tensor is 0, then there exists a vector field U such that this epsilon minus W is equal to del U. So this we have seen now. So by another potential theorem, there exists a U, there exists a vector field U such that epsilon minus W is equal to del U. So that was another potential theorem that we have proved. Okay, so now let us write this statement here. So what we have now is that epsilon is equal to W. So this is epsilon is equal to del U plus W. Okay? And now take the transpose of this. So epsilon transpose is epsilon itself. So you get del U transpose and then W with this. So you add now these two. So you will get that, so plus, so you get 2 epsilon is equal to del u plus del u transpose. So this implies that epsilon is equal to half of del u plus del u transpose. So, so what we have shown is that so what we have shown is that if your del cross epsilon equal to 0, then there exists a vector field u such that epsilon is equal to half of del u plus del u transpose. So actually, I mean, you may wonder where we have used the fact that the domain is simply connected. Okay, so we have used these potential theorems, right? So in the proofs of this potential theorem, you will see that we have made the assumption that the domain is simply connected. Okay, so that is the place where that simply connected assumption is being used. So that is remaining hidden here because I am directly using these potential theorems here. But if you look at the proofs of those things, they rely on that particular fact that the domain be simply connected. So the last thing now is to show the uniqueness of u now. So let us show the uniqueness of u now corresponding to this field here that we have shown here. So uniqueness of u, uniqueness of u corresponding to this epsilon here. So let u tilde be another field, right? Let u tilde be another displacement field, be another displacement field corresponding to epsilon, corresponding to epsilon, corresponding to epsilon. So what we will get is that so we will get that epsilon is equal to half of del u plus del u transpose, and this is also equal to half of del u tilde plus del u tilde transpose. And then if you subtract now, subtract the two, so minus, so you get 0 is equal to half of del of u minus u tilde plus del of u minus u tilde transpose. And so corresponding to a zero strain, so this means this has to be a linearized rigid displacement, right? So this implies now that u minus u tilde is equal to w of t times x plus c of t. So that's what I said, that the displacement is unique up to a linearized rigid displacement. So if you suppress the rigid displacement, then actually the displacement solution will also be unique. So let us just summarize the whole situation here. So let us summarize this particular situation here. That so suppose if you are given that epsilon is equal to half of del u plus del u transpose, then this will imply that del cross epsilon is equal to 0. Okay, so the compatibility relations are satisfied. Conversely, if the compatibility relations are satisfied, then there exists a vector field u such that epsilon is equal to half of del u plus del u transpose. And this vector field u is unique up to a linearized rigid displacement. Okay, so the last point to be made here is that this del cross epsilon is a symmetric second order tensor. Okay, so this will have only 6 independent components. So this del cross epsilon belongs to sim. Okay, so it's a symmetric second order tensor, and so only the diagonal and the components above the diagonal, those are the independent components, and so there are only 6. So there are only 6 compatibility relations because of that. Compatibility relations because of that. And so you must have already seen these compatibility relations in your various books, Deformation Gradient or other books on linearized elasticity. So basically they will directly follow from this del cross. Although the derivations may have been different, but finally the compatibility relations will be the same. So from what you get from this del cross epsilon equal to 0. So we'll stop.